Hello, class. I am starting the 45th lecture. I should have written it up at the top there, except who knows, maybe they'll all be renumbered at some time in the future. Who knows? So anyway, what I wanted to continue with today is the lecture that we sort of ended on last time. We were talking about the reflection coefficient. We're really in chapter 8. Going from 8.5 to 8.7 now, looking at standing wave ratios. We're starting to look at, reflections off impedance mismatches and where the load is mismatched to the line, things like that. So we'll be looking at that just so that you know exactly, what it is that we're doing. If I have, let's say, a waveguide, right? I have a waveguide, and that waveguide is now coming to a boundary, right? And I have a wave that's propagating down that waveguide. All right, let's just say that I've got some type of wave. I probably didn't draw that too well, but whatever. Propagating. One, two, yeah. Oh, well, I'm probably, whatever, something like that. I've got a wave propagating down that waveguide, and it comes to some type of, now this could be a mismatch of impedance between two waveguides. Like I'm connecting a 75 ohm to a 50 ohm waveguide, so coaxial cable, if you wanted to think of it that way. And so if this one had Z sub 0,1, and this had a different characteristic impedance, Z sub 0,2, what we would find at the interface is that we would have a reflection coming back. And of course, that we can figure out what that is, as I mentioned before, both for the current and for the voltage. And of course, the current and the voltage reflection coefficient are 180 degrees out of phase. If you remember the example that I did the last time we had a lecture, I said that the voltage reflection coefficient is going to be Z sub L minus Z sub 0 divided by Z sub L plus Z sub 0. And of course, the reflection coefficient for current is 180 degrees out of phase for that. So the only thing that really changes is that the numerator is Z sub 0 minus Z sub L rather than the other way around, and Z sub L plus Z sub 0 in the denominator. And of course, we did the example where I showed you in the last lecture that those would be 180 degrees out of phase because I did an example with two complex impedances. And so that's what I want to talk about today. Now, what happens here, right, at this interface? Well, let's say that there's and sometimes the reflection coefficient can be positive, sometimes it can be negative. Of course, positive means that it's going to be in phase. Negative means that it's going to be out of phase. And you can have either one of those, but what happens is that there's a reflected wave back along here, right? So let's say that this is my incident wave, the black one that's come in, and then I have a reflected wave that's at a smaller magnitude than that, and perhaps in phase, perhaps out of phase, whatever, and it's going to be reflected back at the same frequency along this waveguide, right? So what's that going to do to the total wave that we have there? Because we've now got two waveforms that are adding together. I'm trying to find my blue. There it is. So we've got two waveforms that are adding together. And let's just look, and they're at the same frequency, of course. So let's just look at what we would have here. Well, we'd have a positive and a negative. So this would be right about here. And then let's look at, you know, here we've got two negatives, so that would be way down here by that point. If I just looked right here, this is going down to 0, but that's a little bit positive, so that would be that point right there. And if I looked over here, I would see that this is 0, but that's so that would be a point right there too, wouldn't it? It's where either one of the two is 0. We could just, so I look at that, that's 0, but this is going to be down here, so that would be right there. And then we can keep doing that as we go up. This is 0, so I know that the next point's going to be there. That's 0, so I know the next point's going to be there. If I look over here, I'm doubling that. So that point would be up there. And then this one would be right here. So let's just connect the dots that I've got there. And what we would have with if that was the only reflection and there was a perfect match on the other end, we wouldn't get any other reflected waves sitting up there. But of course, that's not the case. And what we get is we get a waveform that looks like this. Now that's just for the black incident wave and the red reflected wave, right? Now, if this goes to the other end and it reflects again, what's going to happen is we're going to end up setting up a standing wave, and a standing wave that is going to be changing, but it will fall into an envelope that looks like this. Right? So it's going to fall into this envelope. Oh, no, I've got that backwards, don't I? That's supposed to, that is supposed to be, well, I don't know if it'll be in that much. Let's, anyway, there's an envelope that it falls into. The envelope looks more like this. I think I sort of drew that wrong. Here, let me draw the envelope that you're going to be seeing here. This is what the envelope looks like more. And so what you've got here is you've got, I'll just draw it right here, V min, that's called a node. And then here would be a maximum. This is called an antinode, or V max. So you can see that V min down here and V max, right, are at two different locations. Now, this would change, and we wouldn't if we had a short circuit on the end, right? A short circuit. Before I said that a short circuit is a voltage reflection of -1. And then an open circuit, I hope I'm getting this out. Yeah, I am. Open circuit is going to give us a voltage reflection of +1. Okay. So for those two special cases, we actually just set up one single standing wave in there. Or if I have a totally perfectly matched, if I have no reflection, if my reflection coefficient is 0, you know, what would that give me? So that's what I wanted to look at is these various different cases. We've got the reflection coefficient here. We can see what the reflection coefficient would be. If I did have a perfectly matched case, this would be 0, right? So my reflection coefficient for both my voltage and current would be 0 if I have a perfectly matched case. So for perfectly, and of course I would have no reflection, would I, at that point? So the wave would just be traveling through. It would just travel through. There would be no envelope around it with a V min and a V max. V max and V min would be exactly the same because there would be no reflection. So for a perfectly matched line between these two boundaries here, so 50 ohm hitching up to a 50 ohm coaxial cable, 75 ohm hitching up to a 75 ohm, perfectly matched, we would have a reflection coefficient of 0, right, for both the current and the voltage. I better put my timer on. I have no idea how long I've been going, but I think it's just a few minutes. So I'm trying to get back in the swing of putting these lectures together. There we go. So anyway, and you could see that because like 50 ohm minus 50 ohm, of course you would get that. So that would be perfectly matched. And we would also think that I'm going to define something here. Voltage standing wave ratio, right? The voltage standing wave ratio for a perfectly matched case would have no Vmax and Vmin. Vmax, right, would equal Vmin, right, for a perfectly matched case. Vmax equals Vmin. So my voltage standing wave ratio, which is the ratio of Vmax over Vmin, right? So we know that VSWR is just Vmax over Vmin in the envelope that's established with the standing wave as I get the reflection off here and back. And so for a perfect case, Vmax over Vmin would equal 1. And that would be for a perfectly matched. Now, how do I determine what VSWR is? My voltage standing wave ratio is 1 plus the absolute value of my reflection coefficient divided by 1 minus the absolute value of my reflection coefficient. And so this tells me, and of course, what is VSWR? It's Vmax over Vmin. This happens to be the general equation. So if for VSWR, if I was figuring out my VSWR for a perfectly matched case, right? And I know it'd be 1. Is that the case there? Yes, because that would be 1 plus 0, right? My reflection coefficient for the voltage is going to be 0 divided by 1 minus 0. And so that would give us 1. And so for a perfectly matched case, I would assume that my envelope looked something like this, right? And then I just had a standing wave inside that envelope. And it always stayed the same all the time, moving back and forth, but, you know, basically outlining that. Voltage min, voltage max equals the same. I've got the envelope up there, the envelope up here. We've got a bunch of waveforms moving back and forth inside there, but basically everything is moving through. Okay. Now, what happens if I have a reflection coefficient, let's say 0.3? So this is the reflection coefficient, right? 0. Let's say that I had one for 0.3. I would have a wave now inside my waveguide, trapped inside my waveguide with the reflections that would look something like this. I'm doing this in relative terms, right? So this would be a reflection coefficient of about 0.33, or let's say minus 0.33, something like that. Okay, now if I was going to take this a step further, right? And so now I've got the same thing. And of course, inside here, what's really going on? We've got waves, you know, that are coming down. Oh, God, I drew that one wrong, right? Like this. And we've got other waves that are, because sometimes what's happening is they're not adding together exactly, and they're not. So this is what I get. So if I have a reflection coefficient of about minus 0.33, I'd have my envelope that looked like this. This would be V min, and this would be V max. And then when we put that in there, so we've got a reflection coefficient of this, and this would be a VSWR equal to 1. Now let's say that I had this one here. If we look at the VSWR for minus 0.33, let me just sort of separate this out here. If we looked at it for 0.33, I would have a voltage standing wave ratio of 1 plus 0.333 divided by, now you're saying, no, it's minus 0.333. Yeah, that's what I'm saying. That's why I use minus, because it's the absolute value of the reflection coefficient, isn't it? So 1 plus 0.333 and 1 minus 0.333 gives me 1.333 over 0.667. Does everyone see that? So I've got now a voltage standing wave ratio, or Vmax, probably over Vmin, of something that looks like about 2, right? So this is a VSWR of 2. Now let's take that a step further again, so that I can, what I want you to see is how the wave is changing, how the envelope of the wave is changing. Let's say that we do something that's pretty high. This would be a voltage reflection of 0.8, right? Voltage reflection, and this is what my envelope is going to look like. This is what I want to, well, it would come down in here, but I can't really do that because I've now written the number there. And of course, inside here, we would have a lot of, different waveforms that are going and filling out that envelope. Right, back and forth. This would now be my V min, and this would be my V max. Now, what's my voltage standing wave ratio? And you can see that V min over V max now is much larger than it is here. So we're starting at 1, right? And then we're going to, or we're starting at a reflection coefficient of 0 with a VSWR of 1. Then we're looking at a reflection coefficient of about 0.33 or minus 0.33. I could have made this a minus, but I think I've already made my point. So when we look at this at 0.8, see how we've now got this envelope that is really getting closer and closer to becoming just a single standing wave in there? So my VSWR now is going to be 1 plus 0.8 divided by 1 minus 0.8, and I think everybody can see that that's 1.8 over 0.2, or 9. So as my VSWR goes up, and I probably should have made these all the same size, but I wanted to sort of point it out, the detail, this is going to go up. Now what happens when it's 1? When it's 1, these things touch, and this becomes just a standing wave that's traveling up and down. In fact, what it looks like is a wave like this that goes up and down, and then these nodes just keep going up and down like that, so that if you had an envelope, the thing would all meet like this, right? And of course, that would be a reflection coefficient equal to 1. And I would recommend looking at the Wikipedia page. Actually, they've got some good things on there too to look at that can show you, moving things. 1, and of course this would just be a standing wave, and that would be when everything is reflected back by an open circuit, right? Because an open circuit is going to reflect everything in phase, and a short circuit is going to reflect everything out of phase. All right. So I just wanted to point those out and sort of explain to you what the voltage standing wave ratio is, rather than just saying, here's the formulas and we're just going to work through all these formulas, and then you're not really understanding what the phenomenon is and why we look at voltage standing wave ratios. You know, a voltage standing wave ratio of 1 basically tells you that you have matched the antenna to the line. And yes, you can have VSWR meters, and you can work toward, you have to maybe change the antenna, maybe you have to change the line a little bit, you have to put a transformer in there, a variable transformer, so that you can change it so that you can match those two impedances. And you can do it by stub matching, and that's what I want to show you with the Smith charts at the very end of the course. So let's keep going with this. I think you understand what VSWR is now, and why it's so important. But I want to, I defined VSWR as 1 plus the absolute value of the voltage reflection coefficient, which of course is the same as the current reflection coefficient as far as the, magnitude and the absolute value go. But now what I want to do is I want to look at expanding this equation out. So let's take the VSWR that we have and take it out of the, and take the 1 minus tau sub v out of the numerator and bring it over here. So I've got VSWR, right, 1 times that, minus VSWR times tau sub v, right? And then I'm pretty sure that's a tau. But hey, it could be something else. So I've got that over there, and then I'm going to take the 1 off that side. So minus 1 equals the magnitude. I should put the magnitude here. The magnitude of tau sub v, right? Okay, well, let's take the tau sub v, or this positive VSWR, and bring it over to the other side. So I'm going to have VSWR minus 1 on one side, and I'm going to have VSWR times tau sub v on the other side, plus tau sub v, right? Everybody sees how that works. So what I can do is I can take tau sub v out of that side. So I've got tau sub v times VSWR plus 1. All right. Oh, I'm just going to make that thicker so that you can see that it's there's no minus there. Don't look at the minus. There is not a minus. Okay, so what I wanted to do is I took that out of there, and I've got VSWR minus 1 over here, and I've got tau sub v in the numerator over here. So this really tells me that tau sub v equals VSWR minus 1 divided by VSWR plus 1. Does everyone see how you can use a VSWR meter now to figure out what your voltage reflection is at the interface between your antenna and your delivery line, right? Your coax go into the antenna. So if I have a VSWR meter, I can figure out what my reflection coefficient is, and I can then, work to solve that. And that would also tell me what the impedance mismatch really is too, isn't it? And if I know what the characteristic impedance of the line is, it indirectly tells me what the impedance of the antenna is too, doesn't it? So I think everybody can see that. That's what we are. We're detectives. We use our tools. our mathematics and relationships to figure things out so that we can make a better garbage disposal or refrigerator or rocket to Mars. So let's get back to this. So the reflection coefficient in terms of VSWR or VSWR in terms of the reflection coefficient. We've got that there. I want to do a little example. So let's cut ourselves a piece of our board out here. I don't know if I really needed all that extra part anyway. And do a little example putting numbers to the variables that we have. So here's what I'm going to say. I'm going to say that I've got a characteristic line impedance of 75 ohms. I've got a 5-volt AC line, waveform running through that. And I've got a load impedance of 100 ohms. All right. So the first thing that I want to do is I want to find out what my reflection coefficient is going to be at the interface between those two different coaxial cables or communications channel, however you want to look at it. So that would be 100 minus 75, right? Divided by 100 plus 75. Hope I didn't lose anybody there. I've got the equations for these right up here, so you can see it's Z sub L minus Z sub O, and that's what I've got there. So I've got 25 divided by 175. Let me just get a sip of coffee. Oh my. So that gives me 0.1 COVID-19. Or something went down the wrong pipe. All right. So my reflection coefficient is 0.143. That also tells me what my reflected voltage is, doesn't it? Because we know the voltage reflection coefficient is my reflected voltage over my incident voltage. And we know what our incident voltage is. It's 5 volts. So my reflected voltage is going to be 0.143 times my 5 volts that are going in. And that gives me a reflected voltage of 0.71 volts. Now, I can also say that my characteristic impedance, right, because it's traveling down that line. So that if I know the absolute value of my reflected voltage, I can find out the absolute value of my reflected current, can't I? Right? So I know that my reflected voltage is 0.71. I know that my characteristic impedance is 75 ohms. So if I wanted to find my reflected current would just be my reflected voltage, the absolute value of that, divided by my characteristic impedance. So that's 0.71 volts divided by 75 ohms. And that tells me that my reflected impedance is going to be 0.0095 amps, or 9.5 milliamps. Does everyone see how I did that? And I used the line impedance and everything and the reflected impedance. Right. You know, we can do the same thing with the incident things. We know it's 5 volts and it's 75 ohms. So my current that's going in, I mean, I'll just write this down here for the current that's incident in there. I'll just put it over in the small little spot here. Is just going to be 5 volts divided by 75 ohms. So 5 volts divided by 75 ohms. I don't think I actually did that, but I will right now. 5 divided by 75 gives me 66.6 milliamps. Okay, so that would be our incident current and voltage, and then this would be our reflected current and voltage. Since we've got the reflection coefficient and everything else, we can figure out what the VSWR is too. Why not do that? I mean, I'm right here. VSWR equals 1 plus 0.143 divided by 1 minus 0.143. I think I did do that. Yep, and that gave me 1.143 over 0.857, which turns out to be 1.333. Okay? So I think everybody can see that there is going to, it's not a perfect match, obviously, but it's not the worst match in the world. You know, we would set up a standing wave and thing that would cause a lot of problems. Let's just say if it was a TV signal, you would not be watching that channel right now with that type of interference. It would be a wavy channel. I just want to point out also that this impedance mismatch is what they used to use to block channels. Like, you know, if there was an X-rated channel or whatever on cable and your parents didn't want it, or, you know, it was can't say blocked. It was, what's the term I'm used? Anyway, that waviness that you would see, probably when you were children, they still had that type of, was impedance mismatch. But what happened was when the internet came around, very quickly, everyone realized you could take a roll of aluminum foil, and then you could put that around your TV, not a coaxial cable, because that's a Faraday cage, but you could put it around twin lead, unshielded twin lead, and then run that back as a stub matching variable impedance match transformer, the aluminum foil ball, along the, basically it's tuner wire, you know, two wire twin lead, and you could get the channel to come in. Yeah, that's right. So they had to do away with that because obviously it wasn't working anymore. People could use a ball of aluminum foil and a, you know, tuner antenna chopped down to do it. Then it wasn't any good. All right. So anyway, that's the VSWR for that too. And this is sort of, you know, like I say, an introduction to VSWR. I want to take this just a step further and just talk about something. Your book has a very good explanation of it, but I just want to mention these two identities as we get into lossless lines and standing waves and everything else, is because these will come in handy, is that if you wanted to find the characteristic impedance of a line, the characteristic impedance of that line is just the square root of the impedance of that line open circuited times that line short circuited, right? There's also another, in the next lecture I'm going to do some examples of these. Also, you can find out beta, so that if you want to know what beta is, in a lossless line, there is no alpha, right? Because R prime is 0, so alpha in the propagation constant is 0. There's only a J beta left. So if you wanted to find out what beta was, beta times the length along the line, and we'll use this in an example problem that I'm going to do later on, finding out how impedance changes along, you know, a communications channel. I just want to point this out. So this is going to be the square root of minus the short circuit impedance divided by the open circuit impedance. Now your book has a really good, I mean, that's further along. I think it's up to 8.7, 8.8, something like that. It has a very good example of how you would use these two identities if you could, if you knew what the open circuit impedance was and the short circuit impedance was for a line, you could very quickly figure out what the impedance was. And of course, we're still talking about these in terms of complex impedances, right? We're not talking about real impedances only. We're talking about complex impedances here. And I want to do an example of that. I just don't want to run out of time or whatever. And I see that I just don't have the paper. So I'm going to stop the lecture here because it's been a pretty good discussion of VSWR, what VSWR is, how the reflection coefficient manifests itself in VSWR, how the actual envelope changes, and what VSWR actually means. And like I said, there are two good examples on Wikipedia that they're not interactive in any way. They just like applets or GIFs or whatever that just go over and over again. But they'll quickly show you in a video way what I'm trying to say here too, if you wanted to look at that. Anyway, thank you very much for coming to the 45th lecture. And I'm going to do the 46th lecture in just a minute.